Section 3.4, the first page and a half. We're going to do this pretty quickly. This section is all about applications of derivatives. We examine applications in which derivatives represent rates at which things change. For example, change in the cost of manufactured items per item under given conditions, change in volume of a spherical balloon per inch increase in radius, change in distance from a given point per unit time, etc. Now, the next 4 lines are really just reviewing what we've already done. We have met the concept of an average rate of change of a function over an interval, being the change in y over the change in x. So the average rate of change of f over the interval going from a to a plus h is the change in y over the change in x. And of course, in the denominator, you just get h on the denominator. And then the instantaneous rate of change at a particular x value is given by the limiting case as h goes to 0. We've done all this, and we've met the idea that we call the instantaneous rate of change the derivative. Now, a couple of quick notes about the word instantaneous. Usually when we talk about something being instantaneous, we're talking about instantaneous as being at the same time. But we use the term instantaneous even when x does not represent time. For example, a problem might ask for the instantaneous rate of change in the volume of a spherical balloon when the radius equals 2 centimeters. So our working variable there might not be a time variable, but a variable representing radius. And in fact, the word instantaneous is usually omitted and just assumed. So let's do a couple of quick problems. Write the volume of a sphere as a function of its radius r. You may remember you've met this both in geometry and maybe more recently as a review for the SAT. The volume of a sphere is 4/3 pi r cubed. So we're writing this actually as a function of r, and usually that's just an implicit assumption that that's our working variable, but here we're writing it more explicitly that v is a function of r. Now we want to find the instantaneous rate of change of the volume v, which we've got, with respect to its radius r. Now when you see something like with respect to, well, to its radius r, what that really is asking you to do is to find the derivative with respect to r of whatever it is that asks you to find the rate of change of. And in this case, of course, it's the volume. So what we're trying to find is dv dr. Now, if you look at v, you'll notice that 4/3 pi really is a constant multiple. You know, it's no different than if I had 7 instead of 4/3 pi. It's just a constant multiple. So we can use the constant multiple rule. So it's going to be my 4/3 pi, and then the derivative of what's left, which is r cubed. So we've now got 4/3 pi, and the derivative of r cubed with respect to r is going to be 3r squared. If that seems a little puzzling, just think about what happened if we were trying to differentiate x cubed with respect to x. Well, that actually is really easy. That's 3x squared. So all we've done really here is replace x by r. So when we tidy up our final answer, the 3's are going to cancel, and I'm left with 4 pi r squared. And our units are very important always with rates of change. I've got the rate of change of a volume. So my volume units are centimeters cubed, and then my radius units are centimeters. So my units are actually going to be, it's a little bit strange, centimeters cubed, cubic centimeters of volume per each centimeter increase of radius, or in radius, I guess, a bit more. All right, and we can write that as cubic centimeters per centimeter, but don't try and sort of cancel that to square centimeters, because it doesn't have a lot of meaning. It really is, it's that many cubic centimeters of volume for every centimeter increase in radius. So let's have a quick look at evaluate this rate of change at r equals 1 centimeter. And this is pretty trivial, really. The whole point is just to review your notation again. This is the rate of change of volume with respect to radius at r equals 1. You've come across that notation, or we can just write v prime at 1. So that's going to be 4 pi 1 squared, which is simply 4 pi cubic centimeters per centimeter increase in radius. And then dv dr evaluated at r equals 3, that's going to be the same as v prime of 3, and that's going to be 4 pi times 3 squared cubic centimeters per centimeter increase in radius. Okay, let's zip through the next page. For another example, and that's change in position. So we're now going to consider an object moving in a line where its position s. We often use s for the position function. On the line is a function of time t given by s of t. Suppose s is measured in miles and t in hours, and we have the graph of s against t, and it is drawn. So suppose, for the sake of argument, that the graph of s against t looks something like that. And we calculate the slope at t equals 2. So there's the slope of the curve at that point. And we think to ourselves, well, what would be the units of these? Let's just draw that tangent line in a little better. What would be the units for this slope? Well, if we think in terms of our, rise over run, our rise is measured in miles. Our run horizontal units will be in hours. So the units will be in miles per hour. So what does it represent? Well, it represents the instantaneous rate of change of the position function with respect to t, and is miles per hour. We found the instantaneous velocity at the time t equals 0. So to see this, the average velocity for the journey from time t to time h, we've got, remember, going back to 8th grade, distance over time, we can subtract the positions from time. This is a position at time t plus h. S of t is a position at time t. So that's going to give us our distance, and the time is going to be given by that's going to be t plus h minus t. So the time for that particular little journey, going from time t to t plus h, is given by that. And then, of course, that would be the average velocity. To get the instantaneous velocity, we're going to take the limit as h goes to 0 of that quotient. And that is, of course, the derivative of the position function with respect to time. If you look at that expression, that's the definition of the derivative of the position function. So, okay, so that's a very important result. To get the velocity of a particle moving in a line, you simply take the derivative of its position function. Very important. So let's just make sure we highlight that too. Instantaneous velocity is given by the derivative of the position function. Now let's consider a graph of velocity against time. So suppose, for the sake of argument, that my velocity function, let's suppose it looks like something like that, and I take the slope at t equals 2, and I think about what would be the units for the slope. Well, if I kind of make my little right triangle, the vertical units, its velocity, it's going to be in miles per hour. Horizontal units are going to be in hours. So the units for the slope are going to be miles per hour per hour. And what does it represent? It represents the rate of change of the velocity at this time. And this is actually the rate of change of velocity, has its own name. It is called acceleration. And it will be, in this particular case, measured in miles per hour. And because it is such a common expression, that it does get rewritten in the form miles per hour is written as miles per hour squared. So we've now got the important result that instantaneous acceleration is given by the derivative of the velocity function. And interestingly enough, since the velocity itself is a derivative of the position function, the acceleration turns out to be the second derivative of the position function. And then one quick final consideration. Velocity can be positive or negative since it reflects the direction of travel. So if you're going in the positive direction of travel, then your velocity would be positive. Going in the opposite direction would be negative. In everyday language, though, we don't normally consider that. We use the concept of speed, where speed is defined as being the absolute value of the velocity. And that's it. We will start with example 2 when we next meet.